Welcome, fifth graders, to the Dallas Independent School District STEM Environmental Education Center. We'd like to give a special welcome to the students at Edna Rowe Elementary and to the students at Thomas L. Marsalis Elementary STEAM Academy. Thank you so much for joining us this morning. We wish you could be here in person, but since you can't be here in person, we're going to do our best to make you feel like you're here during a virtual field trip this morning. If you are watching this and have not registered for this field trip yet, you can still do that by going to www.tiny.cc/EEC register. And once you get there, you can fill out a short form to get yourself or your class registered for this field trip. We just use that information for our attendance purposes. This morning's field trip is going to be about forces. During this virtual field trip, students will discover that energy occurs in many forms and can be observed in cycles, patterns, and systems. So students will investigate the effects of force on an object. So we're going to start off today by looking at pushes and pulls with Mrs. Fuller. Next, we're going to explore the force of gravity with Ms. Ramirez. Third, we will explore the force of friction with Ms. Nash. And last but not least, we're going to explore the force of magnetism with me. While we're doing all of that, you can ask us questions, and we encourage you to ask questions. But since this is a virtual field trip, the way you ask a question is by going to www.tiny.cc/EEC-question-answer. And once you get there, you'll fill out a very short form to ask us any questions you have related to forces. You can ask as many questions as you like, and we will do our best to answer all of them in the time that we have with you this morning. So let me stop sharing my screen here and turn it over to Mrs. Fuller, who is going to get us started with pushes and pulls.
Good morning, boys and girls. We're going to be talking about forces and vectors today. And a force is a push or a pull. Now, this is my chicken, Lauren. And Lauren Chicken is going to help me with get the class started today. And she did that by laying an egg. She pushed the egg out of her body. She used a force, push, to get it to exit her body. Now we're going to use the same egg to demonstrate the pull of gravity. So we're going to put the egg right here on our egg. Whoa, look at that. So let's see what Lauren did. Let me see if I can stop the swing of it. And she laid a large egg this morning. Congratulations, Lauren. So gravity pulled the egg down when I put it on the egg sizer. So not exerciser, but egg sizer. So let me put this down. I'm going to put Lauren down too. All right. So when we talk about forces, we're actually talking about vectors. A force is a vector, and two forces of equal magnitude and opposite direction will cancel each other out. Vectors have both size and direction. So the particular vector that we saw there was the vector of gravity, pulling the egg down on the sizer. But Lauren pushed the egg out of her body. So let's think for just a minute about what are some real simple, real close by examples of push and pull. Well, you may have one in your driveway right now. If you have a front wheel drive car, that front wheel drive engine is going to pull the car forward. If on the other hand, you have a real rear wheel drive car, that rear wheel drive is going to push the car forward. So it's two different concepts just in order to get an automobile to go forward. Front wheel drive is going to pull it forward. Rear wheel, this is really hard to say. Rear wheel drive is going to push it forward. Now, when I was a little girl, I read a book called Dr. Dolittle. Some of you maybe have read that also. And there was a character in his book called the Push Me Pull You. It was an animal that on one end had the head of a gazelle, on the other end had the head of a unicorn. And The push me pull you would push one in and pull the other. Well, sometimes we feel that way, that things are pushing and pulling. Let's talk a little bit about Mr. Isaac Newton. He's the second most smart scientist ever born. He lived a long time ago during a pandemic, and they closed his school, and he had to go live out in the country to get away from the pandemic. And while he was there, he came up with three laws of motion. The first law states that an object at rest tends to stay at rest unless acted upon by a net outside force. The second part of that first law is an object in motion tends to stay in motion unless acted upon by a net outside force. So net force, what's the net force? Net force is defined as the sum of all the forces acting on an object, and it can accelerate a mass. And what are the forces? Those are things like what are the pushes and the pulls? Those are things like gravity, wind, friction, mechanical energy. And mechanical energy is an energy that's composed of both potential and kinetic energy. The energy of my hand, magnetism. We've got all different kinds of energies, but it's the net force, the accumulation of all this that can cause an object either at rest or in motion to change. So let's demonstrate one of those right now. This is a beaker, a plastic beaker. It's full of inertia beads, and I'm going to let the force of gravity pull it over, and we're not going to have a net force to stop it. It's going to continue until it hits the floor. Now, as they go over the side of the beaker, I want you to notice that they're not actually striking the side of the beaker. They're actually leaping over it. So here we go. Let's get started here. You see that leaping over the edge? And that happened very quickly, didn't it? And it stopped when it hit the floor. So gravity pulled it, but now it's being pushed up by the floor. So there's inertia. And the second law says that force equals mass times acceleration. And so the force, the push or the pull, is going to be equal to the mass of the object times the acceleration of the object. All right. And I think we've already covered vectors. So let's look at a couple of things. Let's talk about, for just a second, about the human body. The human body does a lot of pushing. So let's think about, it's winter time. A lot of us have a runny nose, and when we sneeze, we push air out of our body to push the pollen that's in our nose out of our body so we don't get sick. When we cough, we're pushing air out of our lungs in order to get whatever's stuck in our trachea out of our body. So there's two pushes. Push of air with our nose, push of air with our cough. So what's another one? The heart. What does the heart do? The heart pushes blood when it beats, when it contracts, it pushes blood through the vascular system of our body to all the body parts so that they can all have oxygenation, so they can have oxygen so the cells can carry out cellular respiration. Okay, think about the peristaltic movement in the alimentary canal in the body. When you put food in your mouth, you chew it up, and the second you start swallowing, you start a push action through your whole body called peristaltic action. And the muscles in your esophagus are going to contract and push the bolus, that's the chewed up food, down into your stomach. And then the muscles in your stomach, after they get through mashing away at that, then they are going, the same movement, peristaltic movement, is going to push it out of the stomach and into the small intestines and so on until it reaches the end. So peristaltic movement is a big push of pushing food through our bodies. Okay, and we've already talked about Lauren pushing an egg out of her body. Okay, let's talk real quick because this is a good one. You'll like this. We've got tension in this spring. We're going to compress the spring to hold tension. And then when we release it, it's going to shoot the little monster head directly up into the air. So that's another demonstration. That was a demonstration of mechanical energy, of stored energy in the spring, and then releasing it into kinetic energy. Forces are very interesting. I hope you have a good time exploring this in your science class. Dr. Gorman will answer any questions you have about pushes and pulls, forces.
Thank you, Mrs. Fuller. Dr. Gorman is having some technical difficulty with his computer, so I'll answer the questions. The first question that came in was, what kind of force is a spring? And it is a pushing force, because a spring wants to push something away from it if you compress the spring. And the other question that came up was, what are some other examples of pushes and pulls? One example of a push is if you push a shopping cart around the grocery store to get your groceries. That is a push. And an example of a pull is if you pull a wagon, that's a pull. All right, now we're going to explore the force of gravity with Ms. Ramirez.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about gravity using a pendulum. So let me go ahead and tell you guys the backstory behind a pendulum. So the story goes that in about the 1500s, a scientist named Galileo was sitting inside a cathedral, and a cathedral is just like a church. So he was sitting in the cathedral, he looked up, and he noticed that the chandeliers were swinging back and forth. Now he noticed some of those chandeliers were doing little swings, and then some of them were doing really big swings. And being the good scientist that he was, he wondered why. So he devised an experiment to help him answer that question. So Galileo is also known as the father of experimental science. So we're going to be studying pendulums today, and a pendulum is just a weight hung from a support that uses gravity that allows that system to swing freely back and forth. So some components of a pendulum would be the support beam, and then the arm. In this case, our arm is going to be a string, and then the bob is going to be the weight at the bottom. So think of some pendulums that you might have around your playground. So let's take a look at our homemade pendulum right here. So you can see this is our support base, and the string is the arm, and then this washer here is called the bob. It's just the weight at the bottom. So what we're going to be doing today is an investigative experiment. We're going to see how does string length affect the number of times a pendulum will swing. So we have one string that is our short one, and it is 5 centimeters. We have a middle string at 10 centimeters, and then a long string at 20 centimeters. So go ahead and make a hypothesis or educated guess. Which string length do you think will swing the most number of times in 15 seconds? And then think about why do you think that way? Now, just so you know, we're going to count a swing as if I put my hand here and I put my bob up at the top, when I release it, it's going to swing forward and then it's going to go back to the starting point. That is one complete swing. So when we do the experiment, I'm going to put my hand behind, and then every time it comes toward my hand, that will be the completion of one full swing. And then I know it's going to be kind of hard for you guys to see it from the computer screen, so I'm actually going to count it as it goes near my hand. That way you guys can help keep track as well. And let me start my timer. We're going to time it for 15 seconds, and we're going to start with the short string first. So I'm going to go ahead and get it in my start position. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. So that one actually did 29 swings in 15 seconds. And hopefully you guys were able to notice that it had short swings and it was doing a lot of them. So I'm going to go ahead and put 29 on our chart here. And we have a little graph like this to record our data. So it says, how does the string length affect the number of swings in 15 seconds? So for 5 centimeters, for our first test, it did 29 swings. So now we're going to skip the middle one, and we're going to go do the long one at 20 centimeters. So let me do our timer again, and I'm going to put it in the start position and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 8, oops. So about 18. So hopefully you guys were able to notice that this one went a lot slower. So it made 18 swings in 15 seconds. So we're going to put that on our chart here. So here's our data. For the first test, the short string went 29 swings. The long string did 18 swings. Now for time constraints, we're not going to do the middle string, but can you guys make an inference? Using this data here, can you make a prediction? What do you think that middle string of 10 centimeters, how many swings do you think it could do? Now also a good scientist would do multiple tests. We only did one test for time constraints, but you can repeat this experiment at home or at school and do multiple tests so that we have enough data to make sure that it's accurate. So the next question is, explain the results. So why did the short string have the most swings? So why do you think that was? And then you can actually repeat this experiment at home, make your own pendulum. So you can use a pencil or a pen, find some string and tie something to it. And you can experiment with different bobs or different objects to put at the end. And then something else that you guys can do is repeat this experiment with different variables. So a variable is what gets changed in an experiment. So for example, how would the mass affect the pendulum swing? So here we have a smaller mass. What happens if we were to put a bigger mass? Would that make a difference? Think about the size and the shape of the bob. What happens if you do, this one's a flat washer. What happens if you put a ball or a cube? Would that affect the pendulum? And then amplitude. Amplitude is the angle. So notice I kind of did a small angle. What happens if you did a big angle? Would that affect the pendulum swing if you were to drop it from here, or even further down? Would that make a difference? So there's different variables that you guys can test to make your own experiment. So now let's go ahead and look at some of our results. So we know that the shorter the string, the shorter the period. And the period is the time it takes to complete one swing. So because the string was short, it took less time to complete one swing. Therefore, it had a higher frequency. And that just means it was able to swing more times in the 15 seconds. Now, the longer string, on the other hand, had a longer period, meaning it took longer for it to do one swing. And because it took longer to do one swing, it had a lower frequency, meaning it did fewer swings in the 15 seconds. So we now know that string length does affect the motion of a pendulum. So the next thing we're going to talk about are what forces are playing a role in this motion. So what are some forces that you can think of, given Mrs. Fuller's discussion? What are forces that you think affect our pendulum? So we have a few. The first one is gravity. So we know that if you guys jump up, gravity is the force that is pulling us back down. So gravity also affects a pendulum. So when I put it up and release it, gravity is trying to pull it back down. We also have friction, and friction is a force that slows motion down. In this case, we have friction in the form of air resistance. So we might not be able to see that air, but we know that it is slowing our swing down. And then we also have, as Mrs. Fuller mentioned, inertia. And inertia is just the statement in Newton's first law that says objects in motion will stay in motion unless another force acts on it. So if there were no forces acting on our pendulum, this pendulum would swing forever. However, we know that's not the case. We know there are forces acting on the pendulum. We know we have gravity trying to pull it down, and we know we have friction in the form of air resistance slowing it down as well. So those are some of the forces that are acting on our pendulum. So think about when you guys are on a playground, what pendulum do you play on and what forces affect you as you're on that pendulum? So hopefully you guys said a swing, and I actually have an example of a pet swing. This is a chicken swing, and animals like to go on swings too. Chickens like to use the swings because it helps them roost. It gets them off the ground, and I think chickens just like to be off the ground so they can watch around and make sure there's no predators around. So this is our chicken swing, and I'm going to show you guys an animal friend. This is going to be Pepper, and she is a blue silky chicken. So she actually uses that chicken swing outside. They get that name blue silky chicken because they actually have blue ear patches over their skin. So hopefully you guys can sort of see that blue skin on her ear. And when you touch her, she is super soft like silk. Now, when she's outside, she likes to go on her swing. I tried putting it on, or tried putting her on it myself, and she kind of jumped off. So I'm just going to show you guys today. But that's Pepper. And now I'm actually going to show you just a couple of videos of some other animals using swings. So let me just share my screen with you guys. It might take just a second to get that going and present that. So we know that a swing is just a type of pendulum. So my first video, as you guys watch the video, be thinking about what forces are affecting the swings and these animals. So this first video are chickens actually using the chicken swing. So think about, again, the forces affecting them. And animals use swings, especially if you go to a zoo, you might see different toys inside the animal habitats. That's for enrichment, just so the animals don't get bored. Gives them something to do. And then in our next video, we have a super cute, it's called a fainting goat. So what do you think is going to happen when he jumps up on that swing set there? And then you notice he falls right off. So they get the name fainting goat, but they don't technically faint, so they don't lose consciousness. What ends up happening is when this breed of goat gets scared or startled, their muscles tense up and they freeze, and that's why he fell to the floor. So that's a super cute breed of goat. And then our next video is a STEM challenge, and it's gonna see if you guys can build a squirrel obstacle maybe at home or at school if you guys have a garden or playground. So as you watch this video, think about forces acting on the squirrel. So that tower that you see is just made out of soup cans, so super easy to make. The swing, you can just use some leftover wood pieces and some string. So it's super interesting and fun to watch animals through a window and see how they're interacting with the different toys that you guys put outside. And you can think about what forces are affecting the squirrel as they jump and swing and climb on things. So it's fun to nature watch. And then my reflection question for you guys is to see if you can find at least 3 examples of pendulums in your everyday life. Think about the forces that are affecting their motion. And in what you're seeing in the PowerPoint are some examples of pendulums. These are seismographs. The big picture is an old-timey seismograph, and then there's a more modern one on the left side. But the way they work, it's based on a pendulum. So if you look at the big picture, there's a string, and it's usually dipped in some sort of ink. And when there's an earthquake, that string will shake rapidly back and forth. And then that's how scientists can detect movement within the earth, so that those earthquakes. So I'm gonna go ahead and stop sharing my screen, and then we're gonna pass it back to Mr. Broughton, and he's gonna answer any questions.
Thank you, Mr. Ramirez. The question that came in was, if I kicked a ball and there was no gravity, what would happen? And that ball would fly through the air, and without gravity to pull it back down, it would probably fly right out of our atmosphere and into space. But without gravity, you might also fly off into space as well, because usually when you kick a ball, you push on the ground to exert a harder force on the ball, and if you pushed off the ground, that you might fly away too. So it's a good thing we have gravity to keep us on the surface of the earth. All right, now we're going to explore the force of friction with Ms. Nash.
Welcome to my classroom, students. And friction is an important thing because that's why we don't roll around. And that's why once we start growing, we can stop. So we all are familiar with friction. We may not have thought of it in that way. So if we push something, we know it's harder to get it started than once it's going. We know that a lighter thing is easier to push than a heavier thing. And that's what friction is. So friction is the force that keeps things from moving and stops them once they start moving. So we have the force, we have the friction, and then we have the weight of the object. And so those are the variables that we're talking about in physics. We have two kinds of friction. We have static friction, and that's the friction that's operating when things are not moving. And then we have kinetic or friction that once it starts moving, the friction is in operation. So friction keeps things stationary, that means not moving. Friction stops moving objects. So what affects the amount of friction? Force, how hard you push or pull, the surface, what you're moving across, and the weight of the object. So we're going to explore those variables, and you can do these same kinds of little experiments on your own. And there's some interesting things that I discovered that I didn't know really. So I have two little ramps I made out of cardboard, easy to make. And I have two different balls. So one's a styrofoam ball and one's a bouncy ball. So the bouncy ball is obviously heavier than that. Styrofoam is all full of air. And I have two little ramps here, and I'm not going to push them. We're going to let gravity pull them down. So gravity is going to be our force. Okay. The surface is the same, but our objects are different weight. So make a prediction. Which one do you think will win the race? And the bouncy ball wins every time. Gravity pulls it down more. Now, here's something else to think about. If I change the surface, so this is a corrugated piece of cardboard I pulled off a box and I put it in my ramp to change the surface. I'm going to take two styrofoam balls this time, and let's see which one wins. Ready? And this one slowed down a little bit. Now I have another piece of styrofoam, of cardboard rather, that I cut in a different way. So the corrugation goes the opposite way. So going down like that, it goes across. So let's see, you think that's going to change our result? Let's see. Pretty much not. Now, here's something really interesting that I discovered. If I have two blocks of wood, okay, and I'll put the cardboard back in. I have two little blocks of wood, and they're very smooth. I'm going to put them on the ramp. Let's see what's going to happen. Nothing happens. Okay. So friction is keeping them from moving. So what can I do? I can change the force. So I'm going to do that. I'm going to raise it up so there's more gravitational force. Now who do you think's going to win this time? And this, to me, this was so interesting because you'd think that this would slow it down. But in fact, this side wins every time. Why? It's because even though this seems really smooth and this feels smooth to us, if we looked at it under a microscope, we would see lots and lots of tiny, tiny imperfections, little ridges. And every time it touches one of those, it slows it down. In here, we've got the corrugation means that it's only touching in some places, so that's why it goes faster. Now, another thing to explore Just try a race between a ball, a styrofoam ball that's really light, and a block that's pretty heavy. Okay, really heavy. So we do that. And again, I have to put it, otherwise our block won't move. So same surface, okay, different weight, different force, and same gravitational force. So which one do you think is going to win this time? And the ball wins. And again, it's because of the amount of surface area touching. In the case of a ball or a wheel, the great thing about the ball and the wheel is that only one point is touching at any one time. And so for that reason, it goes down more quickly than the ball. So to me, that was so interesting. It works every time. Oh, and I have another variable, another kind of surface. And this is my yoga mat. I cut parts of it off. And we use a yoga mat when we do yoga so we don't slip and fall and hurt ourselves on the floor. It holds your feet, grips your feet. So when we're walking around, if it's icy, you might slip and fall, okay? Because that ice reduces the amount of reduces friction. So if you're walking on a sidewalk, you might want to walk on the grass, which has more irregular surface, and you won't fall. On that sidewalk, it's slippery. Water does the same thing. So you may have seen a car slip and slide on a wet road because the water reduces the amount of friction. So let's try that one. Let's compare it to this. So 2 more styrofoam balls. You want to predict who's going to win this race? Let's see. Now you can see the winner. See? Cheating. Okay, here we go. 1, 2, 3. And try again. And this one seemed to win. Okay. And I think it's because it has like little tiny bumps on it, which helps us stand on it. But the ball moves across it really quickly. So it's an interesting thing to do. You can run little experiments of your own. You can make your own little ramps, and you can compare different surfaces, different objects. Okay, remember to, and different amount of force. Okay, so a ramp, the amount of how high you put it changes the amount of gravitational force. So remember to change only one variable at a time to run your experiment. So I hope you enjoyed learning a little bit about friction, and Mr. Broughton will be glad to answer any questions.
Thank you, Ms. Nash. The question that came up was, if I kicked a ball and there was no friction, what would happen? And if there was no friction, I don't think you could kick the ball in the first place. You would just continually fall down and not be able to kick it. But maybe if friction disappeared right after you kicked the ball, somehow I think that ball would just keep going around and around the earth, but so would you, because there would be no friction to ever slow you down. All right, I'm gonna share my screen now, and we're gonna explore magnetism, but we're not gonna use a regular magnet. We're going to use an electromagnet. So let me just get my iPad turned on here. Just takes it a second. There we go, and get my camera on. And yeah, now you can see my triple beam balance right here. I've got a little jar of iron filings. Looks like that inside. That almost looks like it could be potting soil, but that is not potting soil or any kind of dirt at all. That is little pieces of iron that have broken off of bigger pieces of iron. And then I have here a D-cell battery and a battery holder. This yellow wire. And a metal nail that looks like that. And what you do to build an electromagnet is you wrap the wire around the nail like this. I'm going to wrap it 10 times to start. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then I'm going to connect this wire to each side of my D cell battery here. There's one side. And here is the other side. And now this nail should be magnetized, but let's see how magnetized it is. So I'm going to put it in the iron filings, kind of move it around so it can pick up what it can pick up. And maybe I need to get those wires pushed all the way down to the end because it's not picking up anything. Picked up just a tiny, tiny little piece. See if I can get the camera to focus on that. It doesn't want to. There you can see like that little tiny piece. And actually I've done this enough times to know that I'm not even going to measure the mass of that amount of iron filings. That's going to be 0 grams. That was practically nothing. So in my science notebook here, I've got a table set up. So with 10 wraps, the mass of the iron filings was 0. But now let's try 20 wraps. So I'm going to wrap this around 10 more times. So 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And my wire is still connected. Let's put it in the iron filings and see what I'm able to pick up. And there, you can see I was able to pick up a little bit of iron filings. Let's find out how much though. So I'm gonna hold this over the paper and disconnect the wire so it drops off. That turns the electromagnet off. And now you can see on the triple beam balance that the mass is already at 3 grams, and that's because the mass of that paper is 3 grams. So let's find the mass of the iron filings though. If I move that over a little bit to get that back to 0, you can see the mass of the iron filings that I picked up went from 3 to 3.1. So it's 0.1 grams of iron filings that I just picked up with 20 wraps. And it looks like that in my science notebook. Now let's try 30 wraps. So 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. I'm going to reconnect my wire over here. And let me kind of reconnect this side too. It likes to get a little loose after a couple of tries. So I got 30 wraps, put it in the iron filings. And there you can see it picked up quite a bit more, and I actually spilled a little bit right now, but I'll get those picked up here in a second. Just going to disconnect my wire here to get all of it to fall off. Whoops. And the nice thing about if you spill, you can just pick it up with your electromagnet. So there I got the rest picked up. Let me disconnect my wire one more time. And you can see there it's definitely more. I'm gonna have to scoot this over a little bit and see if that balances it. I think I need to go a little farther. This line over here is not quite lined up with the 0. Now, let me get my hand out of the way so you can see that. Almost, but not quite. So just maybe 1 more tenth of a gram. I think that's going to be it. So if I zoom in there, it looks like we're up to 3.6 grams, but we started at 3, remember, so it's just 0.6 grams of iron filings that I picked up. So let me dump those back out. And we're going to wrap it 10 more times and see what happens. So 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. We're at 40 wraps now. Let me reconnect my wire. Looks all good. So I'll put that back in the iron filings. And wow, it's really picking up a lot now. So let's drop that onto the paper before I spill any of it, because it does fall off. And you can see again, it's about that this pointer moved above the 0 because I've got more mass. So I slid that gram piece over a little bit, and I think it's balancing out to 0 again. Maybe just one more 1/10 of a gram. Maybe just a tiny bit more just to get it right at that 0. I think that's it. So let's zoom in. And you can see it's about 3.9. So it's now at 0.9 grams with 40 wraps. Let me dump that back in. Let's see if I can get 50 wraps. I don't have a lot of wire left, but maybe. Or you know what? Actually, we'll just stop right there, because you can see that it is every time I increase the number of wraps, it increases the number of there, that's a little better. It increases the number of or the mass of the iron filings that I can pick up. So now that I've got my table, I can make a graph. So I set up a little graph here. The number of wraps was 0, 10, 20, 30, 40, 50. We didn't get to 50, but that's all right. And here's the mass in grams that I can pick up. So at 10 wraps, it was 0 grams of iron filings. At 20 wraps, it was 1/10 of a gram of iron filings. At 30 wraps, it was 6/10 grams of iron filings. And at 40 wraps, it was 9/10 grams of iron filings. So if I connect my dots here, you can see that as you increase the number of wraps, you do increase the mass of the grams of iron filings that you can pick up. So going back to forces, I increased the magnetic force of my electromagnet by increasing the number of wraps. So you can do a similar project like that at home, but maybe try, instead of a thin wire like I used, try a thicker wire like this. Or I used a D-cell battery, but you could use a C-cell battery instead. See if that makes a difference, or double A, or whatever you have. And here's a different nail it's a smaller nail than the one I used. If I hold them up next to each other, you can see they're not the same. So you could try different variables to see how to create the strongest electromagnet that you can using the materials that you have. All right, now I'm going to stop sharing this screen and switch to my other screen here. And we'll do a quick recap of what we did today. So today we explored forces. During this virtual field trip, students discovered that energy occurs in many forms and can be observed in cycles, patterns, and systems. Students investigated the effect of force on an object. So first we explored pushes and pulls with Mrs. Fuller. Next we explored the force of gravity with Mr. Ramirez. Third, we explored the force of friction with Miss Nash. And we just finished up exploring the force of magnetism using electromagnets. Thank you so much for joining us this morning. We appreciate you taking the time to learn about forces with us. We are not going to see you again until after the break, but After we enjoy our winter break, we hope to see you again during the next field trip for 5th graders. Have a great rest of your day, and we'll see you next time. Goodbye.